Well, hello again. How are you? So in this video today, we are going to be looking at some rules and some kind of commonalities that you will find for almost any dynamics problem, so net force type problem. Okay, there are certain things you're going to need to keep in mind when approaching any problem. The things we talk about in this video will not apply to every single problem, but these are good generalities to look at and to keep in mind when dealing with any problem. Okay, so let's start with this one called net force. The net force, right? In my other force video, I briefly talk about this. Okay, what is net force? Well, it's the sum of all the forces acting on an object. In order to solve these problems, you're going to need to break those forces into horizontal or vertical or some other kind of components, which we'll get to on another time, a little bit later in this video. But just understand that when you say net force equals mass times acceleration, right, you're taking into account all of the forces acting on that object. Sometimes you can have an object accelerating in just one direction, but that doesn't mean forces in another direction or another dimension don't apply to it. It just maybe they cancel out so that it only accelerates in that one direction. With that said, the acceleration of the object is always in the direction of the net force, right? So if my net force is this way, it's going to accelerate that way, even if I have another force that way. If I'm accelerating that way, the net force is that way, okay? Now, going back to what we talked about before, the other thing is you can never, ever mix dimensions. I'm going to have a problem from time to time where I've got forces that are vertical, I've got forces that are horizontal. I cannot put in the same equation these two forces. If I do, I need something else involved to help make it so that they are somehow able to be able to put in the same. It doesn't work. Okay? When creating your equations, you can set a net force equation for just your horizontal and a net force equation for just your vertical. Okay? You can make two separate equations for the same object. Okay? All right. The next thing, when dealing with multiple forces, let's say I have two forces to the right. I'm going to say we have a 10 Newton force and a 7 Newton force to the right. And to the left, I've got a 5 Newton force. Okay? How would I handle something like this? It's all horizontal, so it's all good. Okay? What I would do is I would make sure that the 10 newtons and the 7 newtons are added up, because if they go in the same direction, they must be added up, and I will subtract the 5 newtons. That's how I would set up this equation. Okay? If I had another force going to the left, I'd make sure I subtracted that from this as well. So I'm saying 10 newtons plus 7 newtons minus 5 newtons minus whatever, right? I can change my notation on my math to make sure that's mathematically equivalent, but that's the general idea, okay? You take all forces in one direction, add those up. Take forces in another direction, you can add those up, but comparing this force direction to that force direction, you must subtract. Same direction, add, opposite direction, subtract. All right, cool. Now, we talked briefly about a force. Maybe you have to break it down into its horizontal or vertical components, right? Well, let's take an object like this. Got an object on a nice horizontal surface, but oh no! The force is at an angle, right? That could be somebody pulling on a wagon or a sled, or if it looked something like, just to draw another picture, something like this, right, where the force is pointing kind of down like that. Maybe that's someone mowing their lawn with a push lawnmower, something like that, right? Either way, regardless of how it looks, the force is not clearly defined in either a horizontal or vertical direction. Well, How do we handle that? Basically, what you've got to do is just kind of mathify it for a second. Okay? This is your hypotenuse. This is your x component, your horizontal component, which we oftentimes call x. If that is your angle, and this is your hypotenuse, this is a right angle here, well then that is your adjacent side. So you'll say that the x component of the force is equal to that hypotenuse times the cosine of the angle, right? Because we know that cosine goes with adjacent when we know our hypotenuse. Okay? Similar kind of steps for the vertical, right? Here's our vertical, that is our y component or our vertical component. We know our hypotenuse, here's our angle, that is the opposite side. Opposite side goes with sine, so we're going to stick with f sub y equals f times the sine of theta. Okay? Now, that will be true where you have f of x equals f cosine theta and f of y equaling f sine theta for everything except for one scenario, and that is when you have an object on an inclined plane. Okay, when that happens, it is important that you end up rotating your axes so that your x component is parallel to the surface and your y component, or your y-axis, is perpendicular to the surface. Okay, so instead of horizontal and vertical components, you'll hear parallel to the surface component or perpendicular surface to the surface component, right? You can label that x and y. When that's the case, through some geometry I'm just not going to get to in this video, we'll say that our f sub x equals f sine theta. So it switches, and our f sub y equals f cosine theta, right? So for just for just inclined planes, we switch our trig functions. Everything else, x is cosine and y is sine. All right, so just keep that in mind when we're going through. All right, now something that I've kind of drawn a few times in this video but haven't quite labeled is a free body diagram. A free body diagram. What is a free body diagram? Well, it's a good diagram to sort of represent the forces acting on any given object. Okay? Couple rules. You absolutely must make sure that each force starts at the dot and points away from the dot. Right? So here's an example of a free body diagram. I have a force going that way, I've got a force going up, I've got a force going down at an angle. So depending on the values here, that object is moving in some way, shape, or form, which we can then use to solve for net force equations. We set a net force equation for our horizontal, our x. So we would take this one as is, and the horizontal component of this using those trig functions we just talked about. And for vertical, we take this one and the vertical component of this force that we're talking about, right? And again, we have to make sure that we take into account our positive or negative signs, right? This is going to the right. This is going down and to the left. So we would want to subtract this force and the horizontal component of this force, just like we'd also want to subtract this force and the vertical component of that force, right? It all kind of works together to properly solve this. All right, next thing. Okay, next thing here. Let's talk about weight. Weight is a biggie. Okay, the weight of an object. Sometimes it's easy to get weight and mass mixed up. Mass is not weight. Weight is a force. So when you weigh yourself on a scale, what you're doing is you're measuring how much force you apply to the ground. Okay? So your weight, F sub g, gravitational force acting on you, is your mass in kilograms times the acceleration due to gravity. Here on Earth, that's 9.81. Okay? It's very important. Sometimes they'll give you mass in kilograms, and you've got to convert to weight. To do so, you just multiply by that 9.81 meters per second squared, or 10 if we're dealing with AP. Sometimes they'll give you the weight in newtons. You've got to make sure that you are clear as to what they're giving you, so you don't accidentally multiply a weight by 9.81. Right? You only want to multiply mass by 9.81. Okay. Another common force would be normal force. What is normal force? Well, normal force is the force that a surface applies to an object. Most commonly, you will see normal force being applied from a horizontal surface or from an inclined plane. But let's say this is a vertical wall. I apply my force to this wall. Well, the normal force will be the force the wall exerts on me, which in this case will be that way, right? That's how normal force works. Normal force does not always equal the weight of the object. You've got to take a look, see what forces are acting in that same dimension as that contact between the surface and the object, and make sure that you calculate it properly. So let me give you a quick example of that. I've got two objects, we'll call them object A and object B. They're stacked on top of each other. Maybe it's a cake, I don't know. Right? So there's a normal force that this surface applies on box A. But that surface has to hold the weight of box A and box B. So even though it's just A acting on the surface, the normal force is not just the weight of box B. Sorry, of box A. Right? It has to take into account box B, any other vertical forces that are acting on it, so on and so forth. So you want to set up your net force equation so that it includes your normal force, and go from there to properly calculate your normal force. Okay. Now, where would normal force become important? Well, friction. Okay, we're going to kind of gloss over just the basics of friction real quick. Now, friction is a force that opposes motion. I slide my hand this way, there's a frictional force that way, right? And even if I'm not moving, I'm trying to move it that way, there's a frictional force that way. Now, the amount of friction that's there depends on what the two objects are made of. So their actual material, skin, whiteboard, versus skin and cardboardy part, or skin and paper, paper on paper. It depends on what the object is actually made of. Okay, and that is represented by this symbol, mu. That mu is our coefficient of friction. Okay, it's just a value that tells you how much friction there is between a couple different materials. So we say our frictional force equals that mu times the normal force. Right? So the amount of friction depends on what those materials are made and how much force that the surface exerts on the object. That's basically it, right? You'll need to use those in your grander net force equations. Plug in your mu times normal force. You might need to go into another equation to properly calculate your normal force. They might give you mu. They might ask you to solve for mu. Read the question. Make sure that you got that there. And finally, I want to talk about one special case, and that is called equilibrium. Equilibrium is a special case. Oops, spelled it wrong. Equilibrium. There we go. Okay. Equilibrium is when the net force on an object equals 0. Sorry, forgot my Newton. 0 newtons. Okay. Now, all that means is that the net force equals 0, which means the acceleration on the object is 0. When the acceleration on an object is 0, that object can be either at rest, called static equilibrium, or moving, called dynamic equilibrium. If it's moving, it has to be moving at a constant velocity, which means the same speed in the same direction. Then it's in equilibrium. So for example, if you're on cruise control in your car, you're moving at a constant velocity. You're moving straight, you're at the same speed, your acceleration is 0. The net force acting on that car is 0. On the flip side, if you're just sitting down watching this video, not moving, the net force acting on you is 0. You're in equilibrium. All right, so those are some basic ideas that we need to make sure we take into account when dealing with any problems regarding forces. They work, they mix around, and they're just different tricks and tips to help you solve these problems. There's going to be another video about a few different scenarios that might arise and how to basically handle those scenarios. So I hope to see you then. Have a good one.